M1 family. The Apple Silicon journey began in November 2020 with the introduction of the M1 chip. This was Apple's first in-house processor designed for Macs, built on a 5-nanometer manufacturing process. At its core, the M1 had 8 CPU cores, divided into 4 high-performance cores and 4 efficiency cores. This hybrid design allowed the chip to deliver fast performance while using very little power, giving MacBooks long battery life without fans running constantly. The M1 also integrated an 8-core GPU, a 16-core neural engine for machine learning tasks, and Apple's first unified memory architecture, where the CPU and GPU shared the same pool of high-speed memory instead of separate modules. In 2021, Apple scaled the design into the M1 Pro. The Pro variant increased CPU performance by raising the core count to up to 10, with 8 high-performance cores and 2 efficiency cores. Its GPU options ranged up to 16 cores, doubling graphics performance compared to the original M1. Apple also expanded memory support, allowing configurations up to 32 gigabytes of unified memory. That same year, the M1 Max pushed things further. While it kept the same 10-core CPU design as the Pro, it doubled GPU capacity to as many as 32 cores and increased memory bandwidth significantly. Unified memory support also rose to 64 gigabytes, making it a workstation-class chip for demanding users such as video editors and 3D artists. Finally, in 2022, Apple introduced the M1 Ultra. This chip was essentially 2 M1 Max chips fused together with a high-bandwidth interconnect called Ultra Fusion. It offered up to 20 CPU cores, 64 GPU cores, and support for 128 gigabytes of unified memory. At launch, it was the most powerful Apple Silicon processor to date. M2 family. The next generation arrived in mid-2022 with the M2 chip. Built on an enhanced 5-nanometer process, it featured 8 CPU cores in the same 4+4 performance and efficiency layout as the M1, but with higher clock speeds and improved per-core efficiency. The GPU was expanded to up to 10 cores, giving around 25% better graphics performance compared to the base M1. Memory bandwidth also rose from 68 gigabytes per second to 100 gigabytes per second, and the maximum supported unified memory doubled to 24 gigabytes. The result was a balanced upgrade that extended Apple's lead in battery life and efficiency. In early 2023, Apple introduced the M2 Pro. This chip added more CPU power with up to 12 cores, 8 high-performance and 4 efficiency. Graphics options reached 19 GPU cores, while unified memory bandwidth doubled again to 200 gigabytes per second. The maximum supported unified memory capacity also increased to 32 gigabytes, making it ideal for heavier professional workloads such as Xcode compiling or multi-track audio editing. The M2 Max launched alongside the Pro version. It used the same 12-core CPU design but offered up to 38 GPU cores, with memory bandwidth raised further to 400 gigabytes per second. Unified memory support also increased to 96 gigabytes, giving creative professionals enough headroom for 8K video editing, 3D rendering, and complex visual effects. Finally, in mid-2023, Apple scaled the architecture once again into the M2 Ultra. As with the M1 Ultra, this was essentially 2 M2 Max chips connected with Ultra Fusion. It delivered up to 24 CPU cores, 76 GPU cores, and supported a massive 192 gigabytes of unified memory. The rumored M2 Extreme, with even more cores, never materialized. Reports indicated that Apple canceled it due to cost and complexity. M3 family. The M3 family arrived in late 2023, marking Apple's transition to 3-nanometer manufacturing technology. This smaller process node brought significant efficiency gains and allowed Apple to raise performance without increasing power consumption. The base M3 chip kept the familiar 8-core CPU design with 4 performance cores and 4 efficiency cores, but each core was more powerful than in the M2. The GPU gained up to 10 cores, now supporting hardware-based ray tracing and mesh shading for the first time in Apple Silicon, greatly improving rendering and gaming performance. Unified memory bandwidth also increased to 150 gigabytes per second, with support for up to 24 gigabytes of memory. The M3 Pro represented a bigger shift compared to previous generations. Instead of simply scaling the GPU, Apple rebalanced the CPU core layout. The M3 Pro featured up to 12 cores, but with 6 performance cores and 6 efficiency cores, rather than the heavier performance core ratio of the M2 Pro. GPU options reached 18 cores. Unified memory support rose to 36 gigabytes, with bandwidth at 200 gigabytes per second. This design gave the chip a unique balance, more efficiency cores for tasks like background processes, while still delivering strong overall performance for professional workloads. The M3 Max scaled things further. It featured up to 16 CPU cores, with 12 performance and 4 efficiency cores. The GPU configuration went as high as 40 cores, doubling graphics capacity compared to the baseline M3. Unified memory bandwidth expanded to 400 gigabytes per second, and memory support increased to 128 gigabytes. This made the M3 Max a workstation-class processor suitable for advanced 3D graphics, machine learning, and demanding video production. Notably, Apple never released an M3 Ultra. Instead, the company advanced directly to the M4 family before scaling the design to an Ultra level. M4 family. In May 2024, Apple introduced the M4 chip, first appearing in the iPad Pro before later moving into Macs. The M4 was built on a second-generation 3-nanometer process, delivering higher transistor density and efficiency. It featured up to 10 CPU cores, with a mix of performance and efficiency cores, and a redesigned GPU supporting up to 10 cores. This GPU carried forward hardware-based ray tracing and mesh shading, but with higher throughput compared to the M3 generation. The neural engine was significantly upgraded, capable of 38 trillion operations per second, making it one of the most advanced on-device AI processors at launch. Unified memory bandwidth was raised to 120 gigabytes per second, and configurations supported up to 24 gigabytes of memory. Later in 2024, the M4 Pro was released. This chip scaled the design to up to 12 CPU cores, featuring more performance cores for heavy workloads. GPU configurations reached 18 cores, and unified memory support extended to 36 gigabytes. The Pro variant balanced CPU strength, graphics power, and higher memory bandwidth, making it the mid-range choice in the lineup. At the same time, the M4 Max became the most powerful member of the family so far. It carried up to 16 CPU cores, with 12 performance and 4 efficiency cores. GPU options scaled up to 40 cores, and memory bandwidth rose to 400 gigabytes per second, matching and exceeding the prior M3 Max. Memory support reached 128 gigabytes, ideal for demanding professional users. Benchmarks showed the M4 Max competing with high-end discrete GPUs in creative workloads, while still fitting into slim MacBook Pro designs. As of early 2025, no M4 Ultra has been announced. Apple may choose to release it later for the Mac Studio or Mac Pro, but currently, the lineup ends with the M4 Max. Intel 4004. The Intel 4004, released in 1971, was the first commercial microprocessor in history. It was a 4-bit processor originally designed for calculators, but it proved that a full central processing unit could fit onto a single integrated circuit, containing just 2,300 transistors and running at 740 kHz. It handled simple instructions, one step at a time. While limited in performance, its importance was revolutionary. The 4004 showed that programming programmable logic could replace fixed-purpose electronics, opening the door to general-purpose computing. Intel 8086. The Intel 8086 arrived in 1978 and introduced the x86 instruction set, which would go on to dominate personal computing for decades. It was a 16-bit processor with initial clock speeds of 5 to 10 MHz. Its breakthrough moment came in 1981 when IBM selected the 8088, a variant of the 8086, for the original IBM PC. That decision effectively locked the entire PC industry onto Intel's x86 architecture. From that point forward, nearly all consumer and enterprise machines would build on this foundation, making the 8086 one of the most influential chips in computing history. Intel 80386. The Intel 80386, released in 1985, was the first 32-bit processor in the x86 family. It could address up to 4 gigabytes of memory, a huge leap from its predecessors. One of its biggest innovations was protected mode, which allowed operating systems to isolate memory between applications, preventing crashes and improving stability. This feature enabled true multitasking, letting multiple programs run at the same time without interfering with each other. The 80386 was also backwards compatible, meaning it could still run software built for earlier processors. With these capabilities, it became the foundation for advanced operating systems like Windows 3.0 and Unix variants, pushing the PC firmly into the modern computing era. Intel Celeron. Intel's entry-level processors begin with the Celeron series. Celeron chips are designed for the most basic computing needs. They usually feature a small number of cores and relatively low clock speeds, which means they cannot handle demanding tasks. Typical use cases include web browsing, email, online shopping, streaming standard definition or high-definition video, and light document editing. You will often find them in budget laptops, low-cost desktops, and school devices such as Chromebooks. Because of their limited performance, they struggle with multitasking, gaming, or any software requiring significant processing power. Their main advantage is low cost, but for most consumers, they provide poor value compared to slightly more powerful options. Intel Pentium. One step above Celeron is the Pentium series. Pentium processors were once Intel's flagship line in the 1990s and early 2000s, but today they occupy a low-budget tier. They generally offer higher clock speeds and more cores than Celeron, which allows them to handle smoother video playback, light multitasking, and standard office applications such as Word, Excel, and Zoom calls. They can manage simple games and media tasks more reliably than Celeron. Pentium chips are commonly found in laptops and desktops in the lower mid-range price segment. They remain unsuitable for heavy gaming, video editing, or professional applications, but they provide an acceptable experience for students, office workers, and general users on a tight budget. Intel Pentium Pro and Pentium 2 and Pentium 3. The Pentium Pro, released in 1995, was a processor aimed at servers and workstations. It introduced out-of-order execution, a feature where the CPU could rearrange the order of instructions internally to maximize efficiency and keep its pipelines busy. Although not very successful in consumer PCs due to its cost, it set the stage for Intel's future architectures. In 1997, the Pentium 2 brought these advanced features to mainstream desktops. Packaged in a unique cartridge form factor, it added MMX instructions designed to speed up multimedia processing such as video playback and audio compression. 2 years later, in 1999, Intel followed with the Pentium 3. It expanded on MMX by adding SSE, streaming SIMD extensions, improving performance in 3D graphics, games, and scientific applications. Together, these chips powered the late 1990s internet boom, multimedia applications, and the early rise of 3D gaming. Intel Pentium 4. Launched in 2000, the Pentium 4 introduced the NetBurst microarchitecture. It was engineered for extremely high clock speeds, with some models surpassing 3 GHz, a record at the time. However, this pursuit of raw frequency came at a cost. The Pentium 4 consumed large amounts of power, generated excessive heat, and often performed worse than competing AMD Athlon processors running at lower speed. Although marketed heavily as the gigahertz race, the architecture scaled poorly, forcing Intel to abandon NetBurst in the mid-2000s. The Pentium 4 is remembered as both a commercial success and a technical dead end, highlighting the limitations of relying on clock speed alone for performance gains. Intel Core i3. The first level in the Core lineup is the Core i3. Core i3 processors are considered entry-level within the Core family. Compared to Pentium, they typically feature higher base clock speeds, more cores, and better support for multitasking. Depending on the generation, i3 chips may include between 2 and 8 cores. cores. This makes them capable of running multiple browser tabs, productivity software, video streaming, and even some light gaming. Games such as Minecraft, League of Legends, or other lightweight titles generally run smoothly on i3. However, for demanding modern games or professional creative work, performance will be limited. Core i3 processors are ideal for students, casual users, or office workers who need reliable speed for everyday computing without paying for unnecessary power. Intel Core i5. Next is the Core i5, Intel's most popular mid-range processor. The i5 strikes the best balance between performance and price for most consumers. Depending on the generation, i5 processors can include 4 to 14 cores, higher turbo clock speeds, and often support technologies like hyper-threading. They are well suited for gaming, photo editing, video editing, and other creative workloads at a mainstream level. i5 chips can stream 4K content, run multiple applications side by side, and handle modern games at medium to high settings when paired with a capable GPU. For most home and office users, an i5 provides more than enough performance to last several years, making it the sweet spot in Intel's lineup. Intel Core i7. Above the i5 sits the Core i7. The i7 line is built for users who demand high performance in both professional and personal computing. Compared to i5, i7 processors typically include more cores, up to 20 in recent generations, along with higher base and turbo clock speeds. They also feature strong support for hyper-threading and larger cache sizes, which allow them to handle heavy multitasking and complex workloads. An i7 can run modern AAA games at high or ultra settings when paired with a good graphics card, while also managing tasks like 3D modeling, advanced coding, machine learning experiments, or editing multi-layer 4K video projects. Because of their performance, they consume more power and often reduce laptop battery life compared to i3 or i5 models. Pricing for i7 systems usually falls in the premium category, making them most suitable for professionals, creators, and gamers who need significantly more computing headroom. Intel Core i9. At the very top of Intel's consumer lineup is the Core i9. The i9 series is designed for maximum performance across extreme workloads. Modern i9 processors can include up to 24 cores, combining performance cores for demanding tasks and efficiency cores for lighter background processes. They are intended for enthusiasts, content creators, and professionals who work with the most resource-intensive applications. Typical use cases include 8K video editing, complex 3D rendering, large-scale software compilation, scientific simulations, and running virtual machines or large data sets. i9 chips are also capable of delivering very high frame rates in modern games when paired with a strong GPU. However, their high price and power consumption mean they are not necessary for most users. For general tasks such as browsing or office work, an i9 provides no noticeable advantage over an i5 or i7. These processors are best suited to a small percentage of advanced users who require absolute top-end performance. Intel Xeon. Intel Xeon processors have existed alongside consumer chips since the mid-1990s, designed specifically for servers, workstations, and enterprise computing. Unlike mainstream processors, Xeons prioritize reliability, scalability, and support for advanced features such as error-correcting code ECC memory, which prevents data corruption. Xeons typically have higher core counts, larger cache sizes, and support for multiple CPUs on a single motherboard, making them ideal for data centers, cloud infrastructure, and scientific workloads. While less common in personal PCs, they dominate industries that require continuous uptime and heavy parallel processing, from financial modeling to 3D rendering farms. Intel Atom. Introduced in 2008, Intel Atom processors targeted a completely different market: low-power, ultra-mobile devices. Built with energy efficiency as the priority, Atom chips powered netbooks, tablets, and embedded systems. Their small size and low heat output made them suitable for devices that needed long battery life. While inexpensive and efficient, they offered very limited performance compared to mainstream core processors. Over time, Atom processors found niches in Internet of Things, IoT devices, network equipment, and lightweight computing tasks, but they gradually disappeared from mainstream laptops as consumer expectations for performance increased. Intel X. Intel's Xe architecture represents its modern effort to compete directly in graphics and AI acceleration. Announced in 2020, Xe spans integrated graphics inside core processors, as well as standalone GPUs for desktops and laptops. The idea is to unify Intel's CPU and GPU design under one scalable architecture, capable of serving everything from entry-level laptops to data center AI accelerators. Integrated Xe graphics in 11th and 12th Gen Core processors offer much better performance than older Intel HD graphics, supporting modern gaming and creative applications without requiring a separate graphics card. On the high end, Intel's Arc GPUs are based on Xe technology, aiming to challenge NVIDIA and AMD in both gaming and professional workloads. This step signals Intel's recognition that future computing depends not only on CPUs, but also on powerful graphics and parallel processing. Zen 1 Ryzen 1000 series. In 2017, AMD launched the Ryzen 1000 series, built on the first Zen architecture. This was AMD's comeback after nearly a decade of struggling against Intel. For the first time in years, AMD offered CPUs with high core counts at affordable prices. The Ryzen 7 1800X, for example, delivered 8 cores and 16 threads, which was unheard of in mainstream processors at the time. These chips were manufactured on a 14-nanometer process and used the AM4 socket, which became AMD's long-lasting desktop platform. Zen 1 CPUs brought simultaneous multi-threading, AMD's equivalent of Intel's hyper-threading, allowing each core to handle 2 threads at once. This gave a major boost in workloads like video editing, 3D rendering, and compiling code. While gaming performance wasn't quite as strong as Intel's Core i7 chips in 2017, mainly due to lower instructions per cycle, or IPC, Ryzen CPUs offered much better value for multi-core performance. For PC builders, this meant you could finally get a processor with workstation-like power without paying Intel's premium. The Ryzen 5 1600 quickly became a bestseller for its balance of 6 cores and low price, while the Ryzen 7 1700 and 1800X targeted enthusiasts and content creators. Zen Plus Ryzen 2000 series. In 2018, AMD refined the design with Zen Plus, used in the Ryzen 2000 series. These processors moved to a 12-nanometer process, which allowed for slightly higher clock speeds and improved power efficiency. They also introduced Precision Boost 2 and XFR2, technologies that automatically pushed clock speeds higher under the right thermal and power conditions. Latency was also improved, particularly in cache and memory access, which helped performance in gaming and other tasks sensitive to response time. The Ryzen 7 2700X became the flagship, with 8 cores and 16 threads, and it shipped with AMD's Wraith Prism cooler, which gained attention for its RGB lighting and strong cooling performance out of the box. While Zen Plus wasn't a radical redesign, it polished the first generation and fixed many of the weaknesses of Zen 1. For example, gaming benchmarks showed noticeable improvement thanks to lower memory latency, and the chips maintained AMD's advantage in multi-threaded workloads. For buyers, this was the point where AMD wasn't just the cheaper option, it was starting to become competitive in both performance and value. Zen 2 Ryzen 3000 series. In 2019, AMD released Zen 2 with the Ryzen 3000 series. This was the breakthrough moment when AMD moved ahead in technology. Zen 2 was built on a 7-nanometer manufacturing process, making it the first mainstream desktop processor line to shrink below 10 nanometers. The design used a chiplet architecture, small 7-nanometer CPU chiplets connected to a 12-nanometer I/O die. This allowed AMD to scale cores efficiently without making one massive chip, reducing costs and improving yields. The Ryzen 9 3900X brought 12 cores and 24 threads to the mainstream AM4 socket, while the 3950X went even further, with 16 cores and 32 threads. Before Zen 2, those numbers were only possible on workstation CPUs, costing thousands of dollars. AMD also introduced PCIe 4.0 support, doubling bandwidth for graphics cards and NVMe SSDs, making Ryzen 3000 systems a favorite for enthusiasts who wanted bleeding-edge features. Gaming performance improved as well, thanks to better instructions per cycle and higher boost clocks. The Ryzen 5 3600 became one of the most popular CPUs of the decade, offering 6 cores, 12 threads, and excellent efficiency at a mid-range price. Zen 2 firmly established AMD as the go-to choice for multitasking and productivity, while closing most of the gap with Intel in gaming. Zen 3 Ryzen 5000 series. In 2020, AMD launched Zen 3 with the Ryzen 5000 series, and this was the turning point where AMD finally beat Intel in gaming performance. Zen 3 redesigned the core layout by combining 8 cores and a large cache into a single complex, reducing communication latency between cores. This improved instructions per cycle by around 19%, the largest leap in Ryzen's history. The Ryzen 9 5900X and 5950X became the new flagships, with 12 and 16 cores, while the Ryzen 5 5600X turned into a bestseller for gamers. For the first time, reviewers consistently showed Ryzen outperforming Intel's Core i9 and i7 chips not only in productivity, but also in high frame rate gaming. Another key factor was efficiency. Despite offering more cores, Zen 3 CPUs delivered excellent performance per watt, and they were fully compatible with many older AM4 motherboards through BIOS updates. This meant upgraders could drop a Ryzen 5000 chip into an older system and instantly unlock top-tier performance. With Zen 3, AMD achieved what had once seemed impossible, leading the market in both gaming and multi-threaded workloads, forcing Intel to rethink its strategy. Zen 4 Ryzen 7000 series. In 2022, AMD introduced Zen 4 with the Ryzen 7000 series. This generation required a brand new socket, AM5, ending the long run of AM4. With AM5 came support for DDR5 memory and PCIe 5.0, giving Ryzen access to the latest high-bandwidth technologies. The chips were built on a refined 5nm process, with a 6nm I/O die, pushing efficiency and performance higher than before. The Ryzen 9 7950X led the lineup with 16 cores and 32 threads, while the Ryzen 7 7700X and Ryzen 5 7600X targeted gamers and mainstream users. AMD also introduced X3D models, which used 3D V-cache technology. By stacking extra cache directly on the CPU, AMD dramatically boosted gaming performance. The 7800X3D quickly gained a reputation as one of the fastest gaming CPUs available, often outperforming chips with higher core counts. Zen 4 also improved efficiency, with higher boost clocks reaching above 5 GHz, while still keeping power draw under control compared to rival processors. However, one challenge for buyers was the cost of the new platform. DDR5 memory and AM5 motherboards were initially expensive, making Zen 4 adoption slower than AMD's earlier launches. Zen 5 Ryzen 9000 series. In mid-2024, AMD officially launched the Zen 5 architecture with the Ryzen 9000 desktop processors, known as Granite Ridge. The first models arrived in August 2024, including the Ryzen 5 9600X, Ryzen 7 9700X, Ryzen 9 9900X, and Ryzen 9 9950X. These chips are built on TSMC's 4nm process and bring an average 16% instructions per cycle uplift over Zen 4, along with higher boost clocks and improved power efficiency. Zen 5 maintains support for the AM5 platform, ensuring compatibility with existing DDR5 memory and PCIe 5.0 motherboards. The Ryzen 9 9950X continues to offer 16 cores and 32 threads, but with faster per-core performance compared to Zen 4 flagship. AMD has also confirmed that X3D cache variants of Zen 5 are on the roadmap, aimed at extending Ryzen's lead in gaming performance. This generation strengthens AMD's position not only against Intel's latest desktop CPUs, but also against Apple's M-series and other ARM-based competitors, as efficiency, AI acceleration, and sustained multi-core performance become central to the CPU market. Ryzen 3, Ryzen 5, Ryzen 7, Ryzen 9 tiers. AMD's Ryzen lineup is divided into clear tiers, making it easier for buyers to match performance to their needs. Ryzen 3 is the entry level, usually offering 4 cores and up to 8 threads. It's best suited for basic tasks like web browsing, schoolwork, office applications, and light gaming. While affordable, it delivers more power than older budget CPUs, such as AMD's Athlon line. Ryzen 5 is the mainstream option, often with 6 cores and 12 threads, and sometimes 8 cores depending on the model. These CPUs balance price and performance, making them the most popular choice for gamers and general users. A Ryzen 5 can handle modern games at 1080p, as well as video editing and streaming. Ryzen 7 pushes into high-performance territory. With 8 cores and 16 threads, Ryzen Ryzen 7 chips are aimed at gamers, streamers, and content creators who need strong multitasking power. They often perform at the sweet spot for high-end gaming, especially with X3D cache variants that enhance frame rates. Ryzen 9 is the flagship tier, delivering 12 to 16 cores with 24 to 32 threads. These processors are designed for professionals, creators, and enthusiasts who want maximum performance for workloads like 3D rendering, heavy video production, or scientific computing. While overkill for simple tasks, Ryzen 9 CPUs provide future-proof power for users who need the fastest consumer chips available. Ryzen Threadripper. Launched in 2017 alongside the first Ryzen generation, Threadripper marked AMD's entry into the high-end desktop, or HEDT, market. Threadripper CPUs brought workstation-level performance to consumer platforms by offering extremely high core counts. The first models started with 8, 12, and 16 cores, but later versions scaled all the way up to 64 cores and 128 threads. Threadripper chips are physically massive and require unique TR4, STRX4, or newer TRX50 sockets, along with robust motherboards designed for their power and bandwidth. A hallmark of Threadripper is its huge number of PCI Express lanes, often up to 128 in Pro variants, which makes it ideal for systems with multiple graphics cards, high-speed storage arrays, or specialized expansion cards. For professionals, Threadripper quickly became an Intel HEDT killer, as it provided more cores, better pricing, and competitive single-threaded performance. These CPUs excel in video editing, 3D modeling, virtualization, and scientific workloads. While they consume more power and cost significantly more than mainstream Ryzen chips, Threadripper redefined what desktop users could expect in terms of raw computational capability. In July 2025, AMD expanded the line with Zen 5-based Threadripper 9000 and Threadripper Pro 9000 processors. These models deliver up to 96 cores and 192 threads in the Pro series, support faster DDR5 memory, and offer full PCIe 5.0 bandwidth. With these launches, Threadripper continues to dominate the workstation and HEDT markets, offering performance levels that blur the line between desktop and server computing. Ryzen APUs G series. Alongside standard Ryzen CPUs, AMD also produces APUs, short for Accelerated Processing Units. These combine traditional CPU cores with integrated Radeon graphics on the same chip. APUs are designed for users who need a single processor that can handle both everyday computing and light graphics tasks without requiring a dedicated graphics card. In desktops, Ryzen APUs are marked with a G at the end of the model name, such as the Ryzen 5 5600G. These chips typically feature 4 to 8 CPU cores with integrated Vega graphics. While not as powerful as a standalone GPU, the integrated graphics are capable of running esports titles like League of Legends, Fortnite, or CSGO at reasonable settings. For budget systems, office PCs, or small form factor builds, APUs provide excellent value by reducing the need for extra components. In laptops, Ryzen APUs are even more common. They allow thin and light machines to balance strong CPU performance with decent integrated graphics, making them competitive against Intel's offerings with Iris X. Over the years, AMD has steadily improved their APU graphics, making them some of the strongest integrated GPUs in the market. Mobile Ryzen UHHX series. For laptops, AMD uses a different naming convention to signal performance levels and power limits. Ryzen U series processors are the ultra-efficient models, with lower power draw, usually between 15 and 28 watts. These are designed for ultrabooks, thin laptops, and everyday productivity. Ryzen H series chips are built for high-performance laptops, such as gaming notebooks or mobile workstations. They typically run at 35 to 45 watts, with higher clock speeds and more cores than the U series. Ryzen HX models go even further, offering unlocked performance for enthusiast gaming laptops, sometimes exceeding 55 watts of power for maximum speed. Mobile Ryzen processors range from Ryzen 3 up to Ryzen 9, just like their desktop counterparts, and they scale in cores and threads accordingly. Paired with either integrated Radeon graphics or discrete GPUs, they've become a major force in the laptop market. By 2023, many gaming laptops adopted Ryzen 7 or Ryzen 9 CPUs because of their excellent balance of performance and efficiency. With the steady evolution of APUs and mobile Ryzen processors, AMD positioned itself not only as a leader in desktops and workstations, but also as a strong competitor in laptops, an area once dominated almost entirely by Intel. Fastmath coprocessors. Cyrix began its story in the late 1980s, not with full processors, but with math coprocessors. At that time, Intel's main CPUs, like the 386 and 486, handled standard instructions well, but were weak at floating-point math, which is the kind of calculation needed for scientific software, spreadsheets, and later, games with 3D math. To speed this up, users could buy a separate floating-point unit. The first Cyrix products were the 83D87 and 83S87. These were drop-in replacements for Intel's own 387 coprocessors. The D version paired with the 386DX, while the S version matched the 386SX. Cyrix designed them from scratch, not by copying Intel's layouts, and they often outperformed Intel's equivalents. One reason was that Cyrix used more hardwired logic instead of microcode, which made floating-point operations faster. They also included power-saving features that shut down unused parts of the chip automatically, a clever move at the time. A bit later, Cyrix followed with the CX487, DLC, and CX487S. These matched with Cyrix's own 486 upgrade CPUs, which we will cover next. Essentially, they extended the life of older systems, letting users pair a faster CPU upgrade with a math coprocessor if they needed floating-point power. By the early 1990s, the Fastmath line had built Cyrix's reputation. Faster or cheaper than Intel's parts, compatible enough to drop into existing sockets, and appealing to budget-minded users. This foothold gave Cyrix the confidence to move from being just a sidekick math chip supplier into making full CPUs. CX486 SLC family. In 1992, Cyrix released its first full CPUs, the CX486 SLC series. These were designed as drop-in upgrades for systems that originally used the Intel 386SX processor. The 386SX was a cost-reduced version of the 386 with a 16-bit external bus, so Cyrix built their SLC chips to fit that socket while bringing in the newer 486 instruction set. The original SLC contained a small Level 1 cache of 1 kilobyte, which gave it an edge compared to Intel's own low-end parts. Although it was sometimes nicknamed half a 486, it gave older 386SX machines a big performance lift at a reasonable cost. Cyrix followed this with the SLC2, which was a clock-doubled version. That meant if your system ran at 25 MHz, the internal CPU core could run at 50 MHz, improving performance without changing the motherboard. Then came the SLC/E, a more efficient revision with lower power consumption, which became popular in laptops because it extended battery life. To make upgrades even easier, Cyrix also sold clip-on versions called the SRX2 modules. These sat directly on top of existing 386 processors, effectively turning them into faster 486-class systems without replacing the original chip underneath. It was a clever way for budget users to squeeze more life out of their old hardware. While the SLC family never dominated the market, it found steady use in notebooks and value desktops, where manufacturers could advertise 486 power at lower cost. This marked the point when Cyrix started gaining a reputation as the underdog alternative to Intel. CX486 DLC family. Released. Alongside the SLC series in 1992, the CX486 DLC family was aimed at systems built with the 386DX processor. Unlike the SX version, the DX had a full 32-bit data bus, so Cyrix made the DLC pin-compatible for that platform. The DLC included the same 486 instruction set and a 1 kilobyte Level 1 cache, just like the SLC, but because it worked on a wider bus, performance was noticeably better. At clock speeds of 25, 33, and 40 MHz, the DLC could sometimes outperform Intel's early 486SX chips, especially when price was considered. This made it attractive for users who wanted more speed without replacing their whole motherboard. Cyrix later introduced the DLC2, which added clock doubling, similar to Intel's DX2 series. This meant the CPU core could run at twice the motherboard speed, such as 66 MHz on a 33 MHz bus. For even simpler upgrades, Cyrix made DRX2 modules. These were drop-in replacements for existing 386DX processors, packaged in a way that made installation straightforward. The DRX2 line addressed compatibility issues that early DLC chips had with some cache control signals on older 386 boards, improving reliability. While the DLC TLC family never became a mainstream OEM choice for big brands, it did find success with enthusiasts and smaller system builders who valued the lower price. In particular, the DRX2 upgrades gave many older 386DX users a bridge into the 486 era without major expense. CX486 line. Cyrix entered the mainstream desktop market in 1993 with the CX486S, followed by DX, DX2, and later the DX4100. These were pin-compatible with many existing 486 motherboards, which made them practical drop-in upgrades. The CX486S targeted systems that originally used Intel's 486SX. It implemented the full 486 instruction set and included on-chip Level 1 cache. Its main advantage was compatibility with 5-volt motherboards that early adopters already owned. That meant users did not have to replace the board or power regulation to upgrade. The DX and DX2 versions added higher clocks. DX2 used clock doubling. The motherboard might run at 33 MHz, while the CPU core ran at 66 MHz. This delivered a clear speed boost in everyday Windows and DOS applications without changing the platform. In general, these chips performed slightly below comparable Intel and AMD parts at the same nominal rating, but they were priced aggressively and worked in a wide range of older boards, which was a key selling point for budget builds. The DX4100 used clock tripling on a 33 MHz bus to reach 100 MHz. Despite the 4 in the name, it was still part of the 486 generation, not a 4x multiplier. With proper motherboard support for write-back cache and voltage, the DX4100 could make a mid-range 486 system feel close to entry-level Pentium territory for office tasks and older games, while keeping costs low. External Level 2 cache on the motherboard still mattered for best results, so systems with larger and faster board cache benefited the most. Cyrix 5x86 M1SC. In late 1995, Cyrix released the 5x86, codenamed M1SC. It was designed to plug into standard socket 3 motherboards used by 486 systems. The goal was simple: give 486 owners near Pentium performance without buying a new board. The core was architecturally closer to an enhanced 486 than to a true Pentium, but it added advanced features for the time, like superscalar execution and larger on-chip Level 1 cache. Typical speeds were 80, 100, and 120 MHz. At 100 MHz, real-world performance often matched or beat an Intel Pentium rated at 75 MHz in office and DOS workloads. There were limits. The chip lacked a full Pentium-class floating-point unit design, and some speculative features were disabled for stability in retail parts. That meant gains were biggest in integer-heavy software, while newer titles tuned for Pentium-specific behavior did not always see the same uplift. Even so, for users with compatible BIOS and proper voltage support, the 5x86 was a cost-effective way to stretch a socket 3 system a bit further. Cyrix 6x86 M1. The 6x86, codenamed M1, launched in October 1995. This was Cyrix's first true attempt at a 5th-generation processor to rival Intel's Pentium. It fit standard socket 7 motherboards and was marketed aggressively as a Pentium killer. On paper, the 6x86 had excellent integer performance. In many business and productivity benchmarks, it outperformed Intel's Pentium at the same clock speed. The architecture borrowed concepts usually seen in higher-end designs, such as register renaming, speculative execution, and advanced branch prediction, which allowed it to process Windows and Office software very efficiently. To address the fact that its raw clock speeds were lower, Cyrix and its partners introduced the Performance Rating System, or PR rating. For example, a 6x86 running at 100 MHz might be sold as a P120+, meaning it delivered performance similar to a Pentium 120 in business tests. This system caused some confusion, but became widely adopted by Cyrix, AMD, and others at the time. However, the 6x86 had a major weakness: its floating-point unit. While the integer side was strong, the floating-point performance lagged far behind Intel. This was not a problem for word processors or spreadsheets, but it became critical with the rise of 3D gaming. Titles like Quake, released in 1996, depended heavily on floating-point math, On Cyrix CPUs, Quake ran poorly compared to Intel Pentiums or AMD's K5 and later K6, damaging Cyrix's reputation among gamers. Another drawback was heat output. Early 6x86 parts running at 3.5 volts generated much more heat than comparable Intel chips, requiring larger cooling solutions. Later revisions at 2.8 volts improved this, but the damage to perception was already done. Despite these issues, the 6x86 briefly put Cyrix at the front of the performance charts in business applications, even surpassing Intel in some reviews. For a moment, it looked like Cyrix could truly challenge the market leaders. 6x86. The 6x86L was a refined M1 core aimed at lowering heat and power while keeping the same strong integer performance. Early M1 parts at 3.5 volts ran hot. The L revision moved to lower core voltage and process tweaks. In practical terms, that meant cooler operation, better stability, and easier OEM adoption without oversized heat sinks. Architecturally, it stayed the same class of chip, excellent in office and productivity tasks, still weaker in floating-point heavy 3D games. Most units continued using performance rating labels to signal business app equivalents to Pentium systems. For buyers who did not play new 3D titles, the L parts delivered a quieter, cooler Socket 7 experience with the same everyday speed as the earlier M1. 6x86MX. The 6x86MX, codenamed M2, was the follow-up to the original M1. It kept the same Socket 7 platform, but added the MMX instruction set for faster multimedia operations and expanded the on-chip Level 1 cache compared with the earlier design. In everyday Windows software, this helped close some of the gap against newer Intel and AMD parts at the time. Cyrix continued to use performance rating labels, so a part sold as P200 did not necessarily run at 200 MHz. It indicated Pentium-class performance in business tests. Floating-point performance remained the weak point, so 3D gaming still lagged behind competitors, even though integer workloads felt quick. As the line evolved and moved to new steppings and process shrinks, Cyrix rebranded the family as Cyrix MII. The MII kept MMX support and higher cache, targeted value Socket 7 systems, and emphasized office and multimedia tasks where its strengths showed best. For budget desktops, it offered smooth, everyday use, but it was not the right choice for heavy 3D titles of the late 1990s. Media GX family. The Media GX line took a different path from performance desktops. It bundled the processor core, basic graphics, basic audio, and the memory controller into one platform, aiming to cut both cost and parts count for low-price PCs. Think of it as an early personal computer system on a chip. The core descended from Cyrix's 5x86. Graphics were integrated frame buffer video for two-dimensional desktops and simple games. Audio handled PC-compatible sound without a separate card. Because memory control and I/O logic were integrated, manufacturers could build very inexpensive machines with fewer chips on the motherboard. Performance focused on everyday tasks, word processing, web browsing of the era, and basic multimedia. There was no onboard Level 2 cache like high-end systems of the time, and graphics shared main memory bandwidth, so heavy three-dimensional gaming was not the target. Where it excelled was price and simplicity. Major brands used Media GX to ship sub-$1,000 PCs, opening the door to more budget desktops and small notebooks. This strategy made Cyrix highly visible with value buyers and helped define the late 1990s low-end PC market. Cyrix 3 VIA era. In 1999, VIA Technologies acquired Cyrix's CPU design group. Soon after, VIA also acquired the Centaur team, which had designed the WinChip line. Two paths existed: a Cyrix-designed core, nicknamed Joshua, and a Centaur-designed core, nicknamed Samuel. Joshua targeted higher performance, but drew too much power for the process of the time and struggled to reach stable high clocks. It was cancelled before broad release. VIA kept the Cyrix 3 brand name, but the shipping chips used Centaur's Samuel core for Socket 370 systems. Early Samuel parts emphasized low power and low cost. They were simple, ran cool, and aimed at basic desktop tasks. The first wave lacked on-die Level 2 cache, which limited performance. The follow-up Samuel 2 revision added on-die Level 2 cache, improving everyday responsiveness while keeping the small, efficient design. Later iterations evolved evolved under the VIAC3 branding. From this point, the Cyrix name on desktop CPUs faded. The integrated Media GX line continued separately as Geode under National Semiconductor and later under AMD, while VIA's Centaur-based designs carried the entry-level, low-power torch into the 2000s. Digital Equipment Corporation, Alpha. Digital Equipment Corporation, better known as DEC, created the Alpha processor in the early 1990s. Alpha was a 64-bit RISC CPU family at a time when most mainstream chips were still 32-bit. This gave it an immediate edge in handling large datasets, scientific workloads, and high-end computing tasks. Alpha was designed with speed in mind. It had a very clean instruction set, aggressive clock speeds, and was built to scale up as semiconductor processes improved. For a while, it was the fastest CPU in the world, hitting performance milestones years before Intel or AMD could match. DEC sold Alpha systems mainly to businesses and researchers who needed raw performance. However, Alpha never gained mass market traction because it was expensive and software support was limited compared to x86. When Compaq acquired DEC in 1998, Alpha's future became uncertain. And when Hewlett-Packard later absorbed Compaq, HP decided to kill Alpha entirely in favor of Intel's upcoming Itanium project. That decision marked the end of what many engineers considered one of the most advanced processor designs of its time, Transmeta Crusoe CPUs. Transmeta was a startup that tried to change how CPUs worked in the late 1990s. Instead of building a traditional x86-compatible processor like Intel or AMD, they developed a unique design called code morphing. The hardware itself was based on a very simple, low-power core, while special software translated x86 instructions on the fly. This allowed Transmeta chips, like the Crusoe, to run standard Windows and PC software while consuming much less energy than competitors. The company was heavily hyped before launch. Investors and the media believed Crusoe could revolutionize laptops and mobile devices by offering longer battery life and cooler operation compared to Intel's hot, power-hungry Pentium 3. Early demonstrations showed impressive potential, but when the processors reached the market, real-world performance was disappointing. The translation layer introduced overhead, meaning Crusoe chips often ran slower than expected. Software compatibility was not always perfect, and manufacturers were hesitant to bet on an unproven technology. Transmeta released follow-ups like the Efficient processor, but they never gained major adoption. By the mid-2000s, Intel had improved its mobile processors, reducing power consumption while keeping higher performance. That erased Transmeta's main advantage. Eventually, the company abandoned CPU design and shifted to licensing its intellectual property. What started as a bold challenge to Intel and AMD ended up as one of the most famous cautionary tales in CPU history. Cyrix, Budget x86 CPUs. Cyrix was founded in 1988 and became known throughout the 1990s as a scrappy competitor to Intel and AMD in the x86 processor market. Instead of targeting the high-end, Cyrix focused on budget-friendly CPUs that delivered just enough performance to run Windows PCs at a lower cost. Their chips, like the Cyrix 486 and later the 6x86 series, were often paired with motherboards in value-oriented computers sold at retail outlets. Cyrix CPUs were technically interesting because they sometimes offered higher integer performance than Intel's Pentium chips at the same clock speed. However, they struggled in floating-point performance, which hurt them in 3D gaming and heavy math applications. Still, Cyrix found a niche among budget-conscious consumers and PC builders who wanted cheaper alternatives to Intel. As competition increased, Cyrix faced pressure on multiple fronts. AMD was improving rapidly with the K6 and Athlon processors, while Intel kept scaling the Pentium line. Cyrix lacked the resources to keep up in design and marketing. In 1997, the company merged with National Semiconductor, which used Cyrix designs to target low-power and embedded markets. Eventually, Cyrix technology was folded into VIA Technologies after VIA acquired National Semiconductor's CPU division in 1999. After that, the Cyrix name disappeared, leaving behind a legacy as one of the more memorable underdog brands of the 1990s PC era. National Semiconductor, Geode line. National Semiconductor entered the CPU market by acquiring Cyrix in 1997. But instead of pushing into mainstream desktop competition with Intel and AMD, the company redirected focus toward low-power processors. This led to the development of the Geode line, a family of x86-compatible CPUs optimized for energy efficiency efficiency rather than raw performance. Geode chips were designed for embedded systems, thin clients, set-top boxes, and other compact devices where battery life and heat output mattered more than processing speed. Geode processors stood out because they could run standard PC operating systems like Windows and Linux while consuming very little power. That combination made them appealing for industrial applications, kiosks, and lightweight computing devices. While never a household name, Geode found a quiet but steady role in niche markets. In 2003, Advanced Micro Devices, AMD, acquired the Geode product line. AMD continued to produce and support these chips for years, but they remained a side business compared to AMD's mainstream desktop and server CPUs. As the embedded market shifted toward ARM-based processors, demand for x86 low-power solutions declined. By the late 2000s, Geode gradually faded away, remembered mostly as an early attempt to bring x86 architecture into ultra-low-power environments before ARM completely took over that space. VIA Technologies, Centaur CPUs. VIA Technologies, a Taiwanese company better known for chipsets, made its way into the CPU market in the late 1990s by acquiring Cyrix's remains and Centaur Technology, a small American processor design firm. Through Centaur, VIA developed a line of x86-compatible CPUs aimed at low-power, low-cost computing. These chips, often branded as C3, C7, and later Nano, never competed directly with Intel's Pentium or AMD's Athlon in performance, but they targeted niche markets like embedded systems, thin clients, and small form-factor PCs. Centaur CPUs were unique because they emphasized efficiency, compact design, and integrated features rather than raw speed. For example, some VIA chips included strong hardware-level encryption support years before Intel and AMD mainstreamed those features. This made them attractive for security-focused applications. However, limited performance and weak marketing meant that VIA processors rarely appeared in consumer desktops or laptops. Over time, the rise of ARM processors in mobile and embedded systems eroded VIA's remaining CPU presence. Centaur continued to quietly design x86 CPUs for specialized uses, but by the 2010s, VIA was largely forgotten as a CPU vendor. In 2021, Centaur made headlines briefly when Intel acquired part of its engineering team, essentially marking the end of VIA's role in the x86 market. Though small, Centaur CPUs are remembered as one of the last alternative voices in an industry dominated by Intel and AMD. IBM PowerPC desktop era. In the early 1990s, IBM, Motorola, and Apple formed the AIM Alliance to create the PowerPC architecture. PowerPC was a RISC design meant to challenge Intel's dominance in personal computing. Unlike x86, which was complex and burdened with legacy instructions, PowerPC promised cleaner design, higher efficiency, and strong performance per clock. Apple adopted PowerPC for its Macintosh computers starting in 1994, replacing the Motorola 68000 series. For more than a decade, PowerPC powered every Mac, from the early Power Macintosh to the colorful iMac G3 and professional Power Mac towers. These CPUs gave Apple a unique identity, differentiating their machines from the Windows PCs that relied on Intel or AMD. In some cases, PowerPC chips delivered excellent performance, especially in multimedia and graphics-heavy tasks. IBM also promoted PowerPC as a general-purpose architecture, using it in servers, game consoles like the Nintendo GameCube and Wii, and even the PlayStation 3's cell processor derivative. Despite technical strengths, PowerPC struggled to keep pace with Intel's rapid advances. Heat and power efficiency became major issues, especially in laptops. By the mid-2000s, Apple grew frustrated with the slow development cycle and IBM's inability to deliver competitive mobile chips. In 2006, Apple made the historic decision to switch the Mac lineup entirely to Intel processors. That move ended PowerPC's role in mainstream desktop computing, though the architecture lived on in servers, consoles, and embedded systems. For most people, PowerPC is remembered as the CPU family that once defined the Mac era before Intel took over. Sun Microsystems, SPARC. Sun Microsystems developed the SPARC architecture in the late 1980s as part of the wave of RISC processors designed to challenge traditional CISC designs like x86. SPARC, short for Scalable Processor Architecture, was built with modularity and scalability in mind. It powered Sun's high-performance workstations and servers, which became popular in universities, research labs, and internet infrastructure throughout the 1990s. SPARC systems were known for reliability, multitasking strength, and the ability to handle demanding workloads such as databases business and scientific computing. SPARC's open architecture allowed other manufacturers to design their own implementations, giving it flexibility across different performance tiers. At its peak, SPARC was one of the most widely deployed RISC architectures in the server market, competing directly with IBM's Power Architecture and Hewlett-Packard's PARISC. Sun positioned SPARC as the backbone of enterprise computing, especially for mission-critical environments. However, the rise of cheaper x86 servers and the consolidation of the enterprise hardware market eroded SPARC's share. When Oracle acquired Sun Microsystems in 2010, Spark development continued, but slowed dramatically. Oracle focused on incremental updates rather than groundbreaking innovations. As cloud computing expanded and x86 servers dominated, SPARC steadily lost relevance. Today, it survives only in legacy systems and niche uses, remembered as one of the defining RISC families of the workstation and server era that eventually gave way to commodity x86 hardware. MIPS Technologies, RISC pioneer. MIPS Technologies introduced one of the earliest and most influential RISC architectures in the mid-1980s. The name MIPS stands for Microprocessor Without Interlocked Pipeline Stages, reflecting its streamlined design philosophy. MIPS processors emphasized simplicity and efficiency, which allowed them to achieve high performance with relatively few transistors. This made them cheaper to produce and easier to adapt for different uses compared to more complex architectures like x86. In the 1990s, MIPS CPUs appeared in a wide variety of products. They powered silicon graphics workstations, which were famous for advanced 3D graphics and were used to create visual effects in Hollywood movies. MIPS also found its way into consumer electronics, most famously in the Sony PlayStation and PlayStation 2 consoles, as well as in routers, set-top boxes, and embedded devices. The architecture's flexibility and efficiency made it a popular choice across industries. Despite these successes, MIPS gradually declined as competition grew. Intel and AMD dominated PCS, IBM's Power PC held its ground in consoles and servers, and ARM began taking over the embedded market. MIPS struggled to keep up with development costs and lost key design wins. By the 2000s, the brand was mostly relegated to low-end and legacy applications. Ownership of MIPS changed hands multiple times, and while the architecture still exists, it has little presence in mainstream computing today. It is remembered as a pioneering RISC design whose influence far outweighed its long-term market share. PARISC, Hewlett-Packard. PARISC, short for Precision Architecture, RISC, was Hewlett-Packard's proprietary processor line introduced in the mid-1980s. Designed for HP's high-end workstations and servers, PARISC was built around the principles of reduced instruction set computing, offering streamlined operations for higher efficiency and performance. HP tailored the architecture to excel in scientific, engineering, and enterprise workloads, positioning it as a competitor to Sun's SPARC and IBM's Power processors. Throughout the 1990s, PARISC powered a wide range of HP systems and earned a reputation for reliability and solid performance in mission-critical environments. The architecture evolved steadily, with improvements in clock speed, memory bandwidth, and multiprocessing support. Businesses that relied on HPUX, Hewlett-Packard's UNIX operating system, often ran it on PARISC machines. However, HP eventually faced the same challenge that doomed many proprietary architectures: the rising dominance of commodity x86 hardware. Maintaining a unique CPU line required enormous investment, and the market for specialized RISC workstations and servers was shrinking. In the late 1990s, HP partnered with Intel to create the next-generation Itanium processor, intending it to replace PARISC. Once Itanium became the official future, PARISC development was gradually wound down. Support lingered for legacy systems, but by the 2000s, PARISC was effectively discontinued. Today, it is remembered as a solid, reliable architecture that gave HP control over its hardware ecosystem before being abandoned in the transition to Itanium. Intel, and HP. Itanium was launched in 2001 as a joint project between Intel and Hewlett-Packard, intended to revolutionize the CPU market. Unlike x86 or RISC designs, Itanium was built on a completely new architecture called EPIC, short for Explicitly Parallel Instruction Computing. The idea was that compilers, not the CPU itself, would handle the heavy lifting of scheduling instructions to run in parallel. This promised massive performance gains if software was optimized for it. for it. On paper, Titanium was supposed to replace not only HP's PARISC, but also Sun's SPARC, IBM's Power, and even high-end x86 servers. Intel marketed it as the inevitable future of computing, with the potential to dominate enterprise data centers. Early benchmarks showed strength in specialized workloads, but problems emerged quickly. Titanium was expensive, required entirely new software, and had poor backward compatibility with x86. Developers were reluctant to rewrite applications to take advantage of EPIC features, which left Titanium underused in most environments. Meanwhile, x86 processors kept improving. Intel's own Xeon chips and AMD's Opteron offered 64-bit extensions that let companies keep running existing software with minimal changes. This destroyed Titanium's main advantage. Over the years, Intel released multiple generations, but adoption stayed limited to a shrinking niche of HP servers. By the 2010s, it was clear that Titanium had failed to live up to its promises. Intel finally discontinued the line in 2021. Today, Titanium is remembered as one of the most ambitious and expensive failures in CPU history, an architecture that aimed to replace everything and ended up replaced itself.